Okay, welcome back everyone after the coffee break. Second speaker of today is Giles Gardam from University of Münster, and he'll be talking about Kaplansky's conjectures, and I have a weird feeling that he might have proved some.
Okay, thanks for the introduction, Michal, and for the invitation. It's a real pleasure to be in Newcastle. Of course, it'd be nice to be physically in Newcastle, but this digital substitute will have to do for now. So today I'm going to talk about Kaplansky's conjectures, which are some conjectures about group rings. They're quite old. So I'll start by telling you some things about group rings. Then I'll have some words of warning about conjectures just in general. And then we'll get stuck into Kaplansky's conjectures, what they are, how they're related to each other, what's known about them, how they relate to some other properties or conjectures that you might care about. And then right at the very end, we'll see some new stuff. So yeah, I guess I should say right now that if you already know this story very well, then probably the first 45 or 50 minutes of the talk won't be so exciting for you. Okay, so let's get started. What's a group ring? So I wanted to include this just so we're all on the same page, but probably a lot of you have seen this before. So let G be a group and R a ring. Then we form the group ring by just taking formal sums of ring multiples of group elements, where these sums all have to be finite. And we make this into a ring by defining addition in the sort of obvious pointwise way, I guess, collecting together different ring multiples of the same group element. And the multiplication is just defined by, multiplying together the corresponding ring elements and the corresponding group elements. And then, so for products, it sort of has to extend distributively like this formula that I've written here. Okay, so it's really just, as a set, it's the free R module on G, but we then extend multiplication by the group linearly to the whole group ring in this sort of nice way. So, So of course, this looks kind of naive in a way, but it's something natural and useful. So, first remark is that both the group and the ring embed into the group ring just by picking the appropriate one from the other thing. So if I map a group element to the one of the ring times the group element, then I get an element of the group ring, and multiplying these things is just multiplying as in the group. So this is actually an embedding of the group into the group of units of the group ring, right? So just recall, of course, the units are things which are both left and right invertible in a ring. Okay, so I've got my group embedded, and of course, I can just take one from my group and multiply it by any ring element. And these things, when I multiply and add them, just behave exactly like R. So I have R as embedded as a subring as well. So really, it's honest to say that I've taken a group and a ring and smashed them together to get some new thing which contains both the group and the ring. And by keeping this in mind, I'm allowed to write things like R minus G, where R is a ring element and G is a group element, and that makes sense because there's some implicit ones in that expression. Okay. So, I guess I'm coming at this as a group theorist, so maybe my line of thinking is, well, I have a group and now I can form this group ring, and maybe it will tell me something about the group. Maybe I can now use ring theory to learn about a group. So you might say this is perhaps a little control. A question?
Sorry for being an formalist. For this to make sense, does it require for R to have a unit?
Yes, sorry. Yeah, all of my rings have one, and yeah, they're rings, not rings, as some people would say. Yeah, but that's a good point of clarification. Thanks, Michal. Yeah. Okay, so maybe you say this is a little bit of a contrived way to stitch together a group and a ring, but they're really natural objects of study. This isn't just some obscure algebraic gadget. And I guess sort of ultimately the reason for that is that if you have a G action on an R module, so of course, actually for this whole talk, whenever I say ring, you could just think field. So then an R module, that's just a vector space. So, a group action on one of these things is just the same thing as a module over the group ring. So whenever I have group actions on R modules, it's natural to talk about group rings. So they come up, for example, obviously in representation theory, which is just studying group actions on vector spaces, say. And also if we're doing topology, say we want to compute cohomology groups, and then we've got some chain complex groups acting on, it's sort of natural that the group ring pops up there. Yeah. So I've sort of set things up as group rings with over a ring. But if we've got a particularly nice ring, namely a field, then the group ring has the structure of an algebra, if you know what that is, an algebra over the field K. So for this reason, often one says group algebra instead of group ring. But I'll stick to group ring because I think, from my point of view, that's sort of the more natural way to think about this, even though at the end of the day, my ring R will very often actually be a field. Okay. So just an example of what multiplication, addition, I mean, how these rings look. If I take my group G to be the infinite cyclic group, say generated by the letter T, then the group ring is just finite formal sums of, okay, well, the elements of the group are just powers of T. So I've just got multiples by my ring coefficients of these powers of T, and they have to be finite. Yes, that's just a Laurent polynomial. It's a polynomial where I'm allowing negative powers of T as well, where, again, as always, it has to be a finite sum. Okay, and similarly, I could chuck in more generators for my free abelian group, and then I'll end up with the Laurent polynomials in K unknowns. Yeah, okay. So that's a quick little introduction to group rings. And since we're going to talk about some big conjectures, I wanted to just spend a little bit of time on a more sort of philosophical side of conjectures in group theory. So we're going to see some conjectures that ostensibly apply to all groups, or maybe at least all countable groups or all torsion-free groups. And when we're dealing with these sort of statements, we have to remember this guiding paradigm or dictum of Gromov. So it's said that Gromov has told us that any statement for all countable groups is either trivial or false. So, I mean, the spirit behind this is that if we're trying to say something which should be true for every single group, then we don't really have much room to play with. We've got 3 axioms. There's a multiplicative neutral element in the group. We have inverses and we have associativity. And this is not really much material to get a theory going with. So the idea is that anything that you can prove, that's for all groups, so anything you can prove just using these 3 axioms, that's either got to be something that's pretty obvious or something that's actually, well, false. So you can't prove it. So for example, statements that are true for all groups, say like Cayley's theorem, I think we probably learned in the first group theory course, the groups embed in symmetric groups, or Lagrange's theorem about index just being order of the group divided by order of subgroup. I mean, these things are certainly say we can treat as being statements that are true for all groups, but are trivial. So I think this dichotomy is a good thing to have in the back of our mind, but at the same time, we have to take the statement with a grain of salt. Okay, this meta theorem has known counterexamples. Of course, it's all a matter of perspective. So, I mean, a result which is quite old and maybe you would argue is not super hard, but is still not a completely trivial statement, is that if I take any torsion-free group and I take its group ring over a field, then that's prime in this sense of prime rings. So that tells me that whenever I take 2 elements such that when I put them on either side of if I put them on either side of the entire ring and I get 0, so if A or B is 0 for all choices of R in the group ring, then actually A or B had to be 0 to begin with. I guess this is a really old theorem. So maybe it's not, the proof's not super hard, but I would say it's certainly not trivial. And I would also say it's really a statement, Okay, it's a statement about groupings, but we really need some basic group theory to get this to work. Okay, then the other end of the spectrum, a really nice theorem is, Ian Leary proved that every countable group embeds into an almost finitely presented group. This is a statement about all countable groups, and certainly if anyone claims that this is a trivial theorem, I'd really like to see the trivial proof. Is there a question?
What is an almost finitely presented group?
Very good question. So almost finitely presented is also called FP2. This is a homological finiteness condition. And so, yeah, this is sort of a homological approximation of being finitely presented. So it certainly can't be true that every countable group embeds in a finitely presented group, because we only have countably many finitely presented groups, but we have, and they then only have countably many finitely generated subgroups, but there are uncountably many finitely generated countable groups. Okay, so this theorem can't be true for finitely presented groups. And in fact, it was for a long time, it was an open problem if there existed any group which was almost finitely presented and not finitely presented. And that was the landmark work of Besvina Brady that finally gave us the first example. Okay, so definitely as a non-trivial theorem, which is true for all countable groups. So this dichotomy of Gromov is like a good guiding thing to have in the back of our minds, but it's certainly not something that's to be taken 100% at face value. Okay. So now back to group rings. We have a group and we're trying to understand it by studying its group ring, or we need to do something, some sort of cohomology maybe. It's obviously very nice if we can do something closer to linear algebra. For example, if we could invert elements, if we can, I mean, of course, the best thing that we could possibly do would be if we could take our group ring and embed it into a skew field, like the non-commutative version of a field where everything's still invertible. Or in other words, if we could embed it into a division ring, that would sort of be really nice. But if we have any zero divisors, which are necessarily elements that we can't embed ever, and then this is an obstruction to that, right? So remember, a zero divisor is just something that we can multiply by something non-zero and get zero out. Okay. So if we want to understand group rings of finite groups, say, or groups which have any sort of torsion, infinite groups with some torsion, then there's some bad news straight away. So suppose that the group G has some element G of finite order n, which is at least 2. Then we have this nice little identity which we learned in high school, and using our ability to interpret expressions where we've implicitly got the ring element 1 showing up everywhere. I mean, this is an identity which makes sense and is valid, and it tells us that we always have a non-trivial zero divisor. That is a non-zero zero divisor showing up in our group ring. Okay, so certainly if we want to work with group rings that don't have zero divisors, or you want group rings that we can embed into skew fields, then it's game over the moment there's any torsion. So maybe we say, okay, let's rule that out. And then at least thinking of cyclic subgroups, that seems all nice and well behaved for us, because if we just think of the group ring for the group Z, infinite cyclic group, then this has no zero divisors, because as we've seen, this is just Laurent polynomials. Certainly you can't multiply 2 Laurent polynomials and get 0 out. Even better, we can of course embed in a skew field. Okay, so maybe we could think that this sort of tells us the whole story. The moment you have torsion, you get zero divisors, but otherwise you don't. And so this is what Kaplansky's zero divisor conjecture says. It's a very bold conjecture. It says, let G be a torsion-free group and K be a field, then the group ring KG has no non-trivial zero divisors. Okay, so I'll be stating all these conjectures over fields just for convenience. I mean, this is sort of usually how they're stated. But of course, you might be interested in working with integral group rings, say. That's like a very good basic example of group rings where the ring of coefficients is just Z. Okay, well, in that case, I mean, if you could prove this conjecture for fields, then you'd also be able to conclude the conjecture over Z, okay, because we can just embed the integral group ring in the complex group ring, say, or the rational group ring if you prefer. Okay, so by restricting to fields, I'm not really ruling out too much, okay, without getting too into the details of how we could try and formulate these conjectures in the greatest possible generality. Okay, so in a way, we could say this conjecture is predicting some ridiculously strong local to global property. It says, if I have a group and there are no zero divisors in the group rings of all its cyclic subgroups, then the same thing is true of the group. Okay, so it's pretty crazy to try and go from something about all cyclic subgroups of a group to the group itself. But that's a conjecture. Okay. Yeah, so this conjecture is super, super old. So Kaplansky included it in a 1956 problem list. I think that's the first time that you can see it in print, but I think it was floating around in the air for some time before then. And I think in the USSR, it was known as the Maltsev problem. So here's a little quote I've taken from the 1977 edition of Passman's book on the algebraic structure of group rings, where he says, as we've just seen, torsion gives you zero divisors, but if you don't have torsion, then there's no obvious way of cooking them up. So because of this, and with frankly very little supporting evidence, it was conjectured that if G is torsion-free, then the group ring has no zero divisors. And amazingly, this conjecture has held up for over 30 years. So certainly, this quote seems to suggest that the conjecture was known to the community in the 1940s already, and that it seemed absurd that no one had disproved the conjecture by 1977. So it's certainly even more absurd that this conjecture is made up. No, I mean, I think really, to be fair, the really amazing thing is that the conjecture has been proved in many, many cases, because it's sort of something that starts out with very little evidence. Okay, we know it for Z, for free abelian groups. Early on, we maybe proved it for some other nice groups which are not too far from being abelian. But actually, it's turned out that this conjecture holds for quite a lot of groups, despite having been initially posed on the basis of very little evidence. Okay. Yeah, I wanted to talk about Kaplansky's conjectures, not just Kaplansky's conjecture. So there are two more, and they're also of a similar flavor. They both are conjectures ruling out certain types of elements in group rings of torsion-free groups. Okay, so if I take a unit of my base ring, or I mean, if we're thinking over fields, that's just saying if I take anything that's non-zero in the field, and I take any group element, then their product, this grouping element that's supported on a single group element, then that's just a unit, because I can invert the ring element and the group element, and that's the inverse in the group ring. So certainly that's an easy way of producing units inside a group ring, and that's what we call the trivial units. I also wanted to quickly recall that an idempotent is just a solution to x squared equals x. Okay, so anyone coming from ring theory or operator algebras is probably offended that I stooped to the point of recalling the definition of an idempotent, but I'm a group theorist, and of course it's very difficult to find idempotents inside groups, which are non-trivial. Okay. Yeah, so the three conjectures are on the same assumptions as before: torsion-free group and coefficients from a field. Then we have the unit conjecture, says that there are no non-trivial units. The zero divisor conjecture, again, that's just no non-trivial zero divisors. And the idempotent conjecture, there are no idempotents other than 0 and 1. The only solutions to x squared equals x are the solutions that we knew back in high school. Okay, and all three conjectures are still open. So, yeah, Kaplansky has other conjectures attributed to his name, but these three form like a tight-knit family that are related to each other, and they're usually sort of a triple act in a way. So today I'm just going to focus on these three questions. Okay. So as I've indicated, they're related to each other. And there's a reason that, although I talked about the zero divisor first, I wrote it number 2 on the list, and that's that there are implications between the conjectures. That's what I'll come to now. So the unit conjecture is actually the strongest. It implies the zero divisor conjecture, which then implies the idempotent conjecture. So I think in a way, the zero divisor is the most famous of these three problems. It's obviously something that is up for debate. So I would say that the unit conjecture is less famous than the zero divisor conjecture, but in a way more infamous, because we think maybe there should be counterexamples to the zero divisor conjecture. You know, if we adopt Gromov's philosophy, it doesn't seem like it's trivially true, so that it should be false. So, and if it's ridiculous that we can't disprove the zero divisor conjecture, then maybe we should think it's even more absurd that we don't have a counterexample to the unit conjecture. Okay, so it turns out that these implications are not too bad, not too difficult to show. So I'd like to take a couple of minutes to work through them now with you. And if nothing else, I think once you've seen the proofs, you'll hopefully never forget the order of these conjectures, which one's strongest and which one's weakest. Okay, so each of these statements is a non-existent statement. It says that certain types of, not necessarily nasty, but at any rate, certain types of group elements don't exist. So of course, the way we prove the implications is in the contrapositive. We'll take an idempotent and use it to cook up a zero divisor. We take a zero divisor and use it to cook up a non-trivial unit. Okay. Well, the first of those is completely trivial, and it's not even an exercise in group rings. It's just an exercise in rings, if we could even call it an exercise. If I have a non-trivial idempotent, then well, we know how to factorize x squared minus x, and so that tells me since x is a non-trivial idempotent, it's not 0 or 1. This is a product of two non-zero things giving me 0. So I've used my idempotent to cook up a zero divisor. Okay, so that's pretty easy. Now what about turning a zero divisor into a non-trivial unit? Well, that's a bit harder and actually requires a little bit of group ring theory, but not a lot. Actually, it only needs this little fact that we saw from 1963, which is sort of flying in the face of Gromov's dichotomy. Okay, so we take our non-trivial zero divisors. So suppose that A and B have product 0 and they're both non-zero. Then precisely because of this ring being prime, which is this thing that I stated before, we know that we can find some element of the group ring such that the product BCA is non-zero. Okay, but now if we square BCA, then we have our A and B reunited in the middle of this product, and so we get out 0. So I have something that squares to 0. So now, using difference of two squares, I can easily write down this product of two things, which gives me 1. And so we have non-trivial units. Okay, we have to worry that these things I wrote down are actually non-trivial in the sense that they're supported on at least 2 elements of the group. That's immediately clear unless we're in characteristic 2, where we have to think a little bit, conclude that if they were both singletons, we'd get, we'd have to get some 2 torsion. Okay. But yeah, that's just a very minor technicality at the very end. Okay. So that's how the conjectures are related to each other. I'd like to just include one more easy statement relating these sorts of ideas, which is that as soon as we have the zero divisor conjecture, well, actually, as soon as we have no zero divisors, this is, again, just a statement for rings, not a statement for group rings. Yeah, once we have no zero divisors, then everything that's left invertible is a unit. That is, it's also right invertible. This is, again, just a nice little identity we just write out. If AB is 1, then we can multiply BA minus 1 on the left by A, which yeah, gives us 0. So since we don't have zero divisors, we conclude that in fact BA is also 1. Yeah. So that's how the conjectures are related to each other, and how, once we know the zero divisor conjecture, then finding units just is about finding things that are just invertible on one side. Okay. All right, so now I want to survey a little bit of what's known about these conjectures, but I'm really summoning up an incredibly vast body of math, so I'm definitely not going to be able to do it all justice or include everything on one slide. And also I decided that I'm not including the names on the slide. I'll try and say as many names as possible, but otherwise this would just become really crazy, because I'm really tapping into vast amounts of theory. Okay, so we know Kaplansky's conjecture in certain situations where it's a consequence of other conjectures, or maybe former conjectures, or former problems that were similarly things that we should apply Gromov style skepticism to, because they ostensibly apply to all groups, or all torsion-free groups. Okay, so this unique product property, okay, it's not a conjecture or problem anymore. We know that there are torsion-free groups without this property, but at least for a while, that was an open question. And as soon as we have this very strong property, which I'll talk quite a bit about in a minute, then we conclude we have the unit conjecture. Okay. Yeah, so what is this unique product property? It is what it says on the tin. It says if we have finite subsets of our group and we take that product, there's always something that is uniquely expressible as such a product. So A and B finite subsets, there's some element of the group which can be written as A times B in only one way. Okay, so certainly this property immediately gives us the zero divisor conjecture, because if I take two elements from a group ring, they're both supported on finitely many elements of the group. And when I multiply everything out and collect the terms, there'll be one element of the group where there's no collecting to be done. It only occurs once. So its coefficient is just the product of two non-zero things, and it's therefore non-zero. But this doesn't immediately tell me that I have the unit conjecture, because maybe I have this one unique product and everything else magically cancels out. Okay. Also, it turns out there's a nice little paper of Stranovsky from 1980 telling us that, in fact, a little group theory lemma, we can promote this property of having unique products to the property of two unique products, which is sort of what you'd imagine it is, as long as one of A and B has size at least 2, then this product set has two things which occur uniquely. So if I multiply two elements of the group ring, and they're not both zero or singletons, let's say trivial units, then the product certainly has at least is supported on at least two distinct group elements. Okay. Right. So now I'll say a little bit about the weaker two conjectures, zero divisor conjecture and the idempotent conjecture. So in these cases, we can apply some serious machinery, some sort of more analytic or K-theoretic methods in order to prove these conjectures in many cases, or at least do it with complex coefficients. Okay, so if we have the Atiyah conjecture, then that gives us the zero divisor conjecture. In fact, Linnell tells us quite a bit more than that. We have our dream comes true, and we can embed the group ring into a skew field. So that's really nice. And a similar sort of thing is that if I have the Baum-Kohn conjecture or Farrell-Jones conjecture. So for all these things, I won't have time to get into what they really mean, but maybe you've heard of them or care about them. And if you haven't heard of them before, then the next time you're in a talk and someone mentions them, then you will have heard of them. So anyway, if we have Baum-Kohn or Farrell-Jones, then that gives us the idempotent conjecture over C. Yeah, so if you want to know how these proofs go, you can look in Alain Valet's book. I think maybe he's here. And the implication for Farrell-Jones, that's Bartels Reich. Okay. So I've related this these conjectures to some other big conjectures. Has it actually got us anywhere? Well, yes, because these other conjectures have been established for groups that we care about, especially for groups that we care about as geometric group theorists. So, yeah, I mean, also some of these things had been proved, without going via these conjectures. So some of the statements I'll say can be done sort of more directly. So for example, Bass proved the idempotent conjecture for linear groups. Okay, but certainly we know these big conjectures in many cases. So for example, residually torsion-free solvable groups satisfying Atiyah. I believe that's Linnell. Hyperbolic groups and amenable groups satisfy Baumgarten. I mean, not only amenable, but all the Haar group or 8 amenable groups. So that's Higgs and Kasparov. I mean, hyperbolic groups, that is Meneyev, Yu, and Laforgue. Although previously we could also directly go via Pushnik. Yeah, certainly there's lots of big things that I'm summoning up here. And hyperbolic and cat zero groups satisfy Farrell-Jones. Yeah, so that's Bartels-Luck, Reich, and Bartels-Luck. Yeah, and just a final statement is that zero divisors were sort of proved over time for larger and larger classes of amenable groups. So I think, as we saw, we know that it's true for abelian groups, poly-infinite cyclic groups, as I think Bovdi in 1960, and then we went through a sequence, say Formanek in 73 was super solvable, Farkas, Snyder, and Cliff in 70s and 80s did virtually polycyclic, sort of getting more and more and more and more until finally in, I think 88, there's a paper of Kropler, Linnell, and Moody applying results from Moody's thesis, some K-theory, to show that in fact zero divisor conjecture holds for any elementary amenable group. Yeah, so something that started out as a very speculative conjecture turns out to be true in many cases, and a lot of the time we can conclude it by feeding through some other big conjectures and applying, yeah, looking at these classes of groups that we care about. Okay, so I've certainly left out big bits of maths, so apologies to everyone who I should have mentioned at this point. Yeah. Okay, so now we're going to focus on the unit conjecture a bit. So we've got this unique products property, which is a very sort of like combinatorial flavored group theoretic statement. It's not, it's a very different flavor from, say, talking about Atiyah conjecture or Baumgarten or Farrell-Jones. So, of course, we should wonder, well, we've established it for these groups. How generic are these groups? How many groups have this property? So, a very easy lemma, which we'll prove just because it's a nice little exercise. Once we have an orderable group, then we know we have unique products. This is observed by Botomura and Remtulla. And okay, maybe you care about orderable groups, or maybe you've heard about them. It's the same as groups acting faithfully on the line by order-preserving homeomorphisms, for example. This certainly includes a large class of groups that I really like, which is locally indicable groups. So they're the groups where we have the property that every non-trivial finitely generated subgroup surjects onto Z. Okay, so that includes, for example, torsion-free null-proton groups and torsion-free one-related groups, free groups. It includes, it's closed under extension, so it includes free bicyclic groups. It includes special groups in the sense of Hageland wires, and even something a bit more quirky, like Thompson's group F. That's covered by this. So as a result, we recover Hickman's 1940 theorem. So I guess Hickman is probably the first work on units in group rings, his paper from 1940, which was actually submitted before the war broke out. It tells us that if we have a locally indicable group, then it satisfies the unit conjecture. Okay, so sort of proving the unit conjecture before the unit conjecture was really formulated. Yeah, so now we've factorized Hickman's theorem into a lot of little steps. Instead of just saying locally indicable implies the unit conjecture, we're now saying, well, locally indicable implies left orderable, implies unique products, implies two unique products, implies unit conjecture. But along the way, we've learned quite a lot, and we can apply these results to more groups than Hickman's original theorem. Okay. So how do we use left orderability to cook up unique products? Well, it's a nice little lemma. Okay, just recall, left orderable means that we have a total order on the group such that it's invariant under left multiplication by the group. So take our finite subsets that we need to prove have a unique product and enumerate them in order of the ordering that we have from A1 up to AM and B1 up to Bn. So because the ordering is left invariant, I know that certainly AI B1 is less than AI Bj for any j not equal to 1. So that tells me that the minimal product out of my m times n products is certainly going to be of the form AI times B1, right? And there's just m possibilities now, and they're all different elements of the group. So one of them has to be minimal, and therefore the minimum is unique. But just want to emphasize, the minimal thing won't be A1 times B1 in general, because I'm not assuming that we have a right invariant order as well. I'm just saying it's left invariant. So there might be some mixing up, but suddenly it's still a unique minimal. Okay. Yeah, so this gives us lots of groups that we like, satisfying the unit conjecture, but of course it's not the end of the story. But actually it turns out that finding groups that don't have this product is fairly difficult. So given that we have this lack of sources of candidates even for counterexamples, maybe we could imagine that actually this very combinatorial group theoretic sort of property of having unique products is actually equivalent to the unit conjecture. We have to entertain that possibility. And then I guess this is really raising the question, is there any chance of taking some sort of, more analytic or K-theoretic or some sort of machinery to bear to this problem using some ring theory in some way? Or is the unit conjecture actually just a group theory statement, which has nothing to do with rings and just ultimately boils down to this unique products business, which of course has nothing to do with rings? Okay, so let's now see what we have in terms of groups without the unique products. Okay, so the concept was actually introduced in 64 by Rudin and Schneider. This is actually the same Rudin who wrote the analysis textbooks. So it was an open question for a bit over 2 decades, whether there existed any torsion-free group without unique products. And the first example was constructed by Rips and Segev in '88 using small cancellation. So probably you can believe that this is the sort of theorem that one can try and prove with small cancellation. Obviously, there's a lot of work to be done to pull it off, but we sort of take a presentation, we say what we want our sets without unique products to behave like. We sort of know in advance how we want the products to pair up and where we want to have, how exactly our failure of unique products arises. And then we just need to somehow cook up our relations in such a way that not only do these equations hold between the products of the form AB, but that the whole thing doesn't collapse, that these things are really the elements are distinct in the group, and that the group is indeed torsion-free. Of course, as I said, everything's going to be torsion-free in this talk, except for the obvious group of order 4 that you can see on this slide. And certainly if you have any torsion in your group, then you don't have unique products. You can just take a cyclic subgroup as your finite subset and multiply it with itself. Okay. Yeah, so I think in the Ribson-Segev examples, one of the sets has size 4 and the other is very large. And certainly the presentations that you get out are necessarily like quite big, complicated presentations. Okay. But shortly after this, in the original work of Ribson-Segev, Promislov came along and showed that there's actually quite an elementary way of cooking up failure of unique products. So Promislov showed that this group here has this nice little 2-generated, 2-related presentation, which is in fact an extension of Z cubed by the Klein 4 group, if you like, Z2 times Z2. This very nice torsion-free virtually abelian group actually has a 14-element set whose square doesn't have unique products. Yeah, so this group seems to appear under various different guises, and as a result, it's acquired various names. So hunch event, I guess that's, if you're looking at it from a more sort of geometric point of view, sometimes called the Passman group or Promislov group, if you're coming at it from group rings and these sort of Kaplansky conjectures. It also happens to be the Fibonacci group. I think this is just some sort of random coincidence, but it's isomorphic to one of these Fibonacci groups given by certain little cute presentations. And I think maybe ultimately the reason why this group shows up a lot of the time is it's sort of it's a unique 3-dimensional crystallographic group with finite abelianization. So it's in a sense sort of the first point where you could look for various types of failure. It's sort of the in some sense, it's like the easiest example of a super solvable group, which could potentially be a counterexample to any of these things. And yeah, so I mean, by saying it's 3-dimensional crystallographic group, I'm just saying it's torsion-free and virtually Z cubed. So the only 2-dimensional crystallographic groups are Z squared and the Klein bottle group. They both have infinite abelianization. In 3 dimensions, you get one example like this. In higher dimensions, you get more groups, but a lot of them actually contain this as a subgroup. Okay, I'm rambling a bit. Yeah, so this group somehow shows up quite a bit, and it's not too difficult to cook up failure of unique products in it. Okay. So I said finding groups without unique products is kind of hard, and really I think I've done my homework correctly, and this slide lists every single example that's known to mankind. So following Ribson-Segev, there were further examples in this small cancellation flavor by Steenbok, Grobe, Martin, Steenbok, and Argentsever, Steenbok, cooking up more examples without unique products with, say, additional properties like sort of fitting into a Rips construction. And then there's sort of a second flavor of non-unique products, the things following in the tradition of Promislov. So there's the original Promislov example with this crystallographic group. And then Carter in 2014 generalized this example. You take the presentation and I think you replace one of the 2's with a 2 to the n on both sides of the equation, something like this. So so this generalizes Promislov's example into a family of examples, and it's really like a proper generalization because you, for example, have free subgroups in the higher examples. It's still a serious bit of work to actually produce and verify the sets without unique products, but yeah, this is what Carter did. And then the most recent example is Solberg from her master's thesis in 2018, where you so this is a polycyclic example that you get by somehow specifying how certain products will pair up, and you take the universal group given by corresponding presentation. Okay. Yeah, so these are all the examples we have. It's a pretty small list. If you want to disprove any of the conjectures, then you certainly need to either use one of these groups or add an example to this list. So of course there are one angle of approaching these problems is to sort of think about sort of universal ways that certain equations can be satisfied in groups, and take the corresponding group presentation and then argue about that group. So, of course, if, say, if any of these conjectures is false, then after picking your field coefficients, it really just comes down to the fact that group satisfying a certain presentation has certain elements which are distinct and certain products which are equal and so on. So you can try and attack these problems by not sort of taking one of these groups off the shelf, but maybe thinking about how you want your failure of the property to work, and then trying to argue that that group really has the properties that you want it to have and that it's really torsion-free. So this approach has been done sort of maybe with more emphasis on zero divisors and another conjecture called direct finiteness. That certainly shows up work of Schweitzer, Dichotomy, Yushchenko, and work of Abdullahi together with Tahiri and also with Jafari. Okay. So that's one approach, universal group satisfying some sort of universal universal groups defined by some sort of equations. Okay. But if we think instead taking a group off the shelf and trying to work with it, well, certainly Promyslov's group is somehow the nicest, easiest thing on this list to work with. Very simple presentation, very easy group to understand. So it's not surprising that there's been some serious effort dedicated to trying to understand what non-trivial units could look like in the grouping of this group. So this is really kicked off by a paper of Craven and Pappas in 2013, which is a pretty heroic effort. I think it's like 47 pages in Journal of Algebra, and they really try and understand what non-trivial units in this group could look like, and they're able to give bounds. I mean, a lower bound on the complexity that a unit has to have. They do this by working in. I mean, you take the support of your grouping element and see what its image in the infinite dihedral quotient of the group is, and then look at the word length of those words. So they say if everything goes to something of like 3 or smaller, then you can't have a non-trivial unit. And that work is sort of continued, being continued by other authors like Abdullahi's Zanjania. But sort of the real payoff of the Craven-Pappas result is that after a small conjugation to fix things up, this example of Promislov has length 3. So they tell us that they answered the sort of obvious question that had been waiting to be asked since 88, which is, does this set that Promislov constructed, does it support a non-trivial unit itself? Okay, and Craven-Pappas showed that this is not the case. So if it turns out that unit conjecture and unique products are actually equivalent to each other, then they're not sort of, the converse direction can't be proven in this super, super local sense, where you take your failure of unique products and use that as the support for your non-trivial units. Okay. Right. Okay. So now we're getting towards, right, I had one more quote that I wanted to share. As I said, it's unclear whether the unit conjecture is really something about group rings, whether it's something about rings where we can use ring theoretic methods, or is it just a sort of combinatorial group theory property? And there's an interesting quote from the end of the introduction of Craven-Pappas' paper. To date, it has never been clear whether the unit conjecture is a ring theoretic problem. We hope that this paper suggests that it might be. Okay. So I'm nearly at the end of the talk, and it's time for me to tell you, what's new. What's my contribution to this story? So I'm really happy to be able to announce today for the first time that in fact the unit conjecture is false. So we take this torsion-free virtually abelian group that was studied by many authors, Promislov, for example. The group ring of that group over the field of order 2 has a non-trivial unit it's, yeah, for example, you can do this with a unit that is supported on 21 elements as a group. So yeah, of course, this group satisfies the zero divisors conjecture. Maybe the first thing we're wondering is, well, what about the other questions? Certainly, this group's virtually abelian. It satisfies the zero divisors conjecture. This example is not going to help us disprove the zero divisor conjecture. But I guess we live in one of two universes. Either the zero divisor conjecture is true, in which case we now know that it can't be true for reasons of the unit conjecture. This is not a fruitful way to try and prove it. Or maybe we live in a universe, okay, I mean, a universe where the zero divisor conjecture is false. And this example at least means that we've overcome some psychological barrier to cooking up a counterexample. So of course, finding this unit is a difficult business, but once you've got it, verifying the theorem is really easy. You just have to multiply it out and check that you get one. So an upper bound on how difficult proving this theorem is. It's compute 400 something products and pair them up. But I mean, actually, the proof is not so bad, and it's it's written up. It's about 2 pages of algebra to verify that these that these units really multiply to give one. So I guess the moral of the story is that the unit conjecture turned out to be just a question in group theory, and it's not really we can't hope to prove it using methods of ring theory, so that's the end of that story. Are there any questions?
What is the element?
So obviously it's a little bit complicated because otherwise someone would have found it before. But it has some nice, it has some nice symmetry. Obviously you can't have too much symmetry. I guess if it had too much symmetry, it would probably tell you that you disprove zero divisors or something like this. You can't square to 1, for example. But it's sort of...
it seems like you don't like to reveal the secret, and I'm sure
no.
This paper in the annals, in a 1 page, just giving the element alpha minus 1 and the multiplication, and keep the secret for you, how you got to it. But why did you look for such a long element, and specifically in this specific group? That seems to be very interesting.
Yeah. Well, I guess I didn't really set out trying to understand zero divisors, but I guess or unit conjecture, but I guess I wanted to see if there's anything, that I can sort of cook up related to some other questions. Yeah, I'm being very vague. Obviously it would be really nice to disprove direct finiteness, which I can't do yet, but that's sort of what led me to trying to understand units of group rings. If I could just quickly say like something about what it looks like. We have this structure as an extension. So, I really work with the structure of the extension. So everything I can write, as, I picked my polynomials or Laurent polynomials to be correct in the grouping of the kernel. So alpha I can write, obviously in a unique way like this. Oops. And these polynomials are really nice and symmetric in a certain sense. They're not too symmetric, but they have lots of symmetry. So in fact, the inverse of alpha is defined by taking the exact same polynomials, but sort of shifting them around a little bit. And the polynomials themselves have sort of rotational symmetry inside cubes. And all of this is sort of combines together in a really nice way, such that when you multiply them out, the polynomials that correspond to A and to B already vanish instantly, regardless of what the polynomials actually are, provided that they have the right symmetry. Yeah, but then obviously it still needs to work out. And I mean, I think it's a bit of a miracle at the end of the day, but it works.
Now, Giles, can you hear me?
Yes, but you're quite quiet.
Okay. I wanted to ask two things. What about the group of units of this group ring? Is it very big? You've found one unit, but like, is there a free group of units inside the
So
unit?
I don't know. Yeah, I believe there's actually a very old theorem that tells you that any non-trivial unit has to be infinite order. But yeah, it would be obviously nice to know that, because it would really show that that the group of units is very, very different from the group itself, whereas the unit conjecture predicts that they should be the same after taking a multiplication with a direct product with the units of the ring, yeah, of the field.
Yeah. And what about the coefficient field of two elements? What have you thought about the field of three elements?
Yeah, I think there is a lot harder. I think for one thing, you probably have to look a lot further, and I mean, obviously, this extra freedom makes it a lot harder to try and to get everything to line up right. I mean, of course, I would really love to have been able to do this in the integral group ring, and I guess my example exploits the fact that we're in characteristic 2 a lot, and it doesn't lift in the obvious way to the integral group ring. And I've really tried quite a bit to make it work in the integral group ring. So who knows? I mean, maybe the unit conjecture just is true if we look at the integral group ring. But I guess my feeling is probably those non-trivial units are out there. It's just that they're quite a bit harder to find.
So it's still conceivable the integral group ring has a non-trivial unit. That's not ruled out by Atiyah or Baum-Kohn or any of those.
No, I mean, the unit conjecture is really only susceptible to this unique product stuff. I mean, I might be overlooking something, but I believe that it's only known to be true in cases where we know the group has unique products.
Was your construction computer assisted?
I had the same question.
Well, I mean, it's 2021. We use computers to go to the pub. We use computers to buy groceries, and we also use computers to do mathematics. Yes, so it is computer assisted, but I mean, you don't need a computer to work through the proof to actually verify this example. And I should add, actually, I mean, Promyslov's example was constructed by a computer. So, I mean, for the majority of the history of these questions, people have been attacking them with computers.
Well, when Promyslov's example first came out in 1988, I actually wrote some computer code of my own to check it. I know it could have been, it can be checked by hand, but it was fun at the time to write some computer code to check it.
Yeah, perhaps I should actually, something worth noting is that, often things turn out to have been lying just beyond reach in a sense. And I mean, this is definitely the case here. Craven Pappas proves that there's no non-trivial unit whose length in their sense is, in terms of, the word length in the dihedral quotient, that they do it for up to 3. And in fact, this example has length 4. So, I mean, they say in their paper, I think, that trying to, boost their computation to cover length 4 would be just a gigantic computation that no one would ever really, that would be, I guess, impossibly difficult.
So do you think that maybe you could use okay, I don't really know to which extent you used or to which extent your proof was computer assisted, but do you think that perhaps you could generalize that to find examples in some slightly different settings?
Yeah, I certainly think that should be possible. But yeah. Maybe I should also say that, I mean, you can take this unit and construct a universal group given by the way that the products line up, right, in the style of that people have approached. And actually, if you do this, possibly up to like a Z factor that always shows up, I mean, you really get the same group back. So in a sense, this group is like already defined by this unit in this group ring, in a sense.
Oh.
So you can't even somehow abstract the algebra to attack the other problems.
All right. Do we have any questions?
One more
Yes,
question.
we do.
Hello. I just wonder whether, is there any magic behind this number 21 in your theorem? The length of the support is 21?
I thought a little about the numerology, but I don't think there's any real significance. I mean, yeah, it's a multiple of 7, and so is 14, which shows up in Promislov's paper, but I think this is just sort of, just a random coincidence. Yeah.
Can I ask a question to everybody? Is anyone old enough to have ever met Kaplansky other than me?
Yeah, I've met Kaplansky. George Willis here.
Right.
Well, when he was director of MSRI, I think a lot of people met him, right? Was that the late 80s?
Yeah.
Okay, so I met him in 69 when he was at Queen Mary College for a semester or for a term or something. And yeah, so he's great at a party. Has anyone ever heard him sing? No?
No.
Yeah.
And when he was director of MSRI, I think he made a point of meeting the people who came to the centre at a party. There was a party, and he
but
made a point of going along and meeting people.
But he wasn't performing in those days.
No.
Right. No, very funny guy.
Well, if we don't have any questions that are directly relate to the talk, perhaps we could leave this kind of discussion after the talk. So thank you, Giles, for the talk. It was really nice. I will admit that this was the first time I saw a talk on group rings that actually I was able to understand whole. So good job on that.
Thanks, it was a pleasure.
Yeah. Thank everyone for coming.
Thank you. It was a nice talk as well as a very nice result.
Yes, thank you very much. Very much appreciated.
Weeks.
Even if you did use a computer.
Right. Thank you one more time.